Yo, homies, back, ready to go. Spring break, killer. Couple good days, though. There were a couple good days. All right. First thing. So now we're official. We're officially done. Never see you again. Well, I'll see you again, maybe. Okay. Maybe police reports, I'll read your name. You never know. Okay. So after Inslee made his decision, he then handed it to OSPI, which is the Governing Board of Education, and they'll hand something to our district, which they did. Of course, I'm a little frustrated by this. Our district got it midweek, last week, spring break week, and they're not going to give us an update on the information till Thursday. So some of you are going, what about graduation or this or that? I don't know anything. I know less than you do. Okay, I do know Thursday, which we all know probably means Friday or Monday because they'll be behind. But supposedly the latest, greatest information from the district is supposed to come out then. Okay, several of the better teachers, administrators are getting together and coming up with a plan of attack. Notice I said better teachers, so that means that leaves me out. I don't want to be part of that stuff. Okay, second thing, so update from the district coming Thursday. Our plan of attack. We are on day 10 of nuclear. This will be the last, well, tomorrow will be the last day. But this is our last day of new stuff. So tomorrow, which would be Tuesday, there'll be a test on nuke. All right. It will be open notes. I'd really prefer no open Google, and you know what I mean by that. No, somebody, well, I'll use the Yahoo or Bing or your mama or whatever. Just use your notes, please. Okay? So that's the second thing. The very last video we did was on fission. Okay? We had no homework on that, so there's nothing for me to go over on that homework-wise. All right, next thing. How about I spell it right? Oh, poop skin. Schedule for the week. Having a hard time writing. I had a good spring break, I guess. I hope you did too. Okay, so Monday, which is today, I'm going to talk about fusion, not fission, fusion. Tuesday, you'll take the nuke test. There'll be a very small video on Tuesday going over the homework from Monday night, very small amount of homework. Remember, I'm really backing off on you. Go over the homework, talk about the upcoming test, and then on Tuesday, I'd prefer you take the test. Okay? Wednesday, part of the video will be grading the test. And we're starting a brand new chapter called reaction rates. Reaction rates are about how do you make something go faster or slower. Okay, how do you speed it up? Guys, I'm really sad about this. We had one of the best labs of the year with reaction rates. You'd have thought I was a magician. Truly, you would. It's a great lab. Every year they love it. It's called the Iodine Clock Reaction Lab. There's just no way we can do it. I can't even get in the school to touch the chemicals. I mean, I'd like just to play with them. Thursday, we will continue on reaction rates. Okay, we'll continue. And Friday, it's all part of reaction rates. I want to wrap all this up together. And it goes on more than just Friday. But Friday's main emphasis is what we call the cube problem. Okay, so there's our plan of attack for the week. Go over fusion today, nuke test Tuesday, Wednesday, Thursday, Friday. Okay, so next thing. Since there's no homework to go over, please pull out your notes and title it Fusion. Okay, let me get my notes out. Fusion. Now, yeah, typical teacher. Start to do something. Well, wait, I want to backtrack. The last time we were together, we talked about fission. And that's splitting of atoms. Okay, Energy Northwest, out there at the Hanford area, Energy Northwest is a nuclear power plant, and they use a process called fission. And a lot of places take uranium-235 and they bombard it with neutrons. And one of these neutrons hits it just right. The cue ball in the game of pool, if the cue ball hits just right, don't the balls scatter? I think it's called the break. Okay, so we want this to basically break that guy. So there's our cue ball. Smack! What it breaks into could be a variety of things. Okay, remember this is fission, splitting. There's a little cesium. And remember, we have our original neutron that keeps going, and we pick up 2 more. So now we have 3 neutrons that go off and split. And remember we called that a chain reaction? If there's a critical mass, enough fuel to keep these guys going, they'll go split, 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 and it goes crazy. And the ultimate way this worked, this side weighed more. This side technically weighed less, not a lot, okay, but that weight we lost, that mass we lost, remember we called that our mass defect, and it's just a small amount. We lose a little bit of weight, just a little bit. But if you remember right, that little bit of weight, we run it through Einstein's equation, E equals mc squared, and we get energy. And we get, boy, we get a lot of energy. Okay, so that's why they do it. Now remember, some of the problems are the radiation coming off, the radioactivity, the storage of this stuff, the half-lives are very, very long, all of that. Fusion. You know, the running joke is you always want to be rich, you want to be the next Bill Gates, the next, who's the Amazon guy? The bald guy. Just cheated on his wife. They divorced. Criminy sakes. What anyway? I think he's the richest man there is in the world. You come up and figure out how to do fusion on a scale that's reproducible in any country, anywhere. Those guys, that their money is pocket change to you. I'm telling you right now, you want to be the richest person right there. Figure out now. The idea of fusion is fine. We can do it. It's the sustaining of it for a long period of time. Fusion is the joining of smaller nuclei. Nuclei is it's just an atom. Okay, we call it a nuclei, just an atom. To make larger stuff, larger nuclei, larger atoms. Okay, essentially all fusion is doing is combining atoms. Okay, push them together and boom, you get a bigger one. Okay, you're taking 2 snowballs, put them together and you get a bigger snowball. Okay, sometimes you've heard this word, fusing them together. So to fuse something is to make it come together. Right now, over me. Who sings that? Okay. The stars out there, okay, however many there are, there's like endless amounts of stars. And the closest star to us has a personal name. We call it the sun. All the stars in the sun out there, our sun is a star. They all rely on fusion. Okay? They all use fusion. So what they do is basically they have a ton of hydrogen. Now see, it's number 3. Hydrogen normally weighs about number 1. So this guy's called an isotope. He weighs a little bit more. He has more neutrons. It's no big deal. This is called tritium. Okay. Here's another hydrogen. This one only weighs 2. So it's another isotope. This one's called deuterium. And it takes quite a bit of energy, but if you squeeze those 2 together, if you go push, 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 boom, you actually get helium and a neutron. Our sun is comprised of hydrogen and helium. And you actually, instead of using tritium, you can use 2 deuteriums. It's just a little harder to do. But you can do 2 deuteriums to get helium. Okay? Tritium's pretty safe. Deuterium's pretty safe. Helium's pretty safe. This seems like a good process. Okay? I'm liking this. I'm liking this. In one day, the energy from the sun Okay? The energy from the sun. One day. That's me reading a book. Okay? All right, soaking up some UV rays, going to be all tan, maybe get a little cancer, all the good things in the world, okay? In one day, the energy from the sun reaching the earth equals all the energy from the sun. One day reaching the earth equals all the energy ever used by humans on this planet. One day versus all the energy ever used. Okay? So what I'm saying is the sun is mega, mega, mega powerful. Remember, if I could make it go away, how long till we know? Be about 8 minutes. You got 8 minutes to do what you're going to do. I'd run to the fridge and eat something really bad. Yeah, I would. Oh, yeah. Oh, yeah. Okay. So now continuing on about fusion. Here's how powerful fusion is. Fission. Remember splitting? If you had 1 kilogram of uranium-235, okay, that's 2.2 pounds. Not 2.21, that's 2.2 pounds. If you had 2.2 pounds of uranium, okay, you can all lift 2 pounds. Come on, that's not that much. The energy from that is equal to combustion, remember burning 2 million kilograms of coal. So basically 2 pounds of uranium is equivalent to burning 2 million kilograms of coal. Well, here's where you're going to be blown away. 1 kilogram of hydrogen. Remember? This is fusion. Hydrogen is pushed together. Push them together. 1 kilogram of hydrogen, which we have plenty of hydrogen. Oh, we got tons in the ocean. I mean, guys, we more than we'd ever need. Okay, got a little excited there. This is 20 times more energy than up there. The idea, if you can make fusion work on a proper scale, 1 cup of water has enough hydrogen atoms to power a car forever. Enough hydrogen atoms. The energy you would get would power your car forever. Okay? Now, one of the drawbacks to fusion, in order to start fusion, remember we take these guys and we squeeze them together? In order to start that, to first push them together, you need a tremendous amount of energy. Tremendous amount of energy to push it, to first start it. Okay? Some people kind of joke is that you need a fission reaction to start a fusion reaction. So that's one of the drawbacks. One of the other drawbacks, when this fusion process starts going, as you know, this sun is warm. It is more than warm. It is mega, mega hot. If we could truly do this, make fusion and keep it in a box, because we want to control it, we would need to be able to handle temperatures of about 200 million Kelvin. The problem lies right here. We cannot make a container that can handle 200 million Kelvin. So here's the problem with fusion. Yes, we can do it. Yes, we can start it up. Yes, we can get the reaction going. And then it goes for a little while, and it gets so hot, it melts down whatever we have it contained in, and the reaction stops. That's the problem. Okay? I know that certain places have tried using electromagnetic processes. So basically keep the fusion like a ball of energy right there, and nothing, it touches nothing. Basically, it's got a box with magnets all around it, and this thing is levitating like a magician levitates a person, so that it never touches his side, but even then it still gets so hot it eventually melts it, shuts the whole reaction down, and boom. Okay, various places are trying different ideas, but that's the problem with fusion. We can do it, we can start it, we can get it going, and we cannot contain it long enough to power plants. Okay? Here's why fusion would be awesome, though. I told you deuterium, there's plenty of it. Plenty. 2, products not radioactive. When you're done, the stuff you get is completely safe. No one's worried about it. Third thing that makes it cool. These are all reasons why fusion is spectacular. Okay? The reaction can be stopped at any time. We can stop it. Boom, done. In fission, let's say we want to stop it and something goes wrong, the product will actually melt down. It'll get out, it'll escape, and it's dangerous. Chernobyl in Russia had a problem. The uranium got so hot it melted through, and it went down, 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 and some people call it elephant's foot. It kind of melted down, and it was way down in the basement, and it's highly radioactive. It kind of looks like an elephant's foot. That's a terrible elephant's foot. Okay? And if we could do fusion, more energy, then we'll have, then I'm just going to put needed. There'll be more energy than ever needed. More. Okay? So we're going to go back in time. I don't know, I was about a junior in college. These two gentlemen, Dr. Pons and Dr. Fleischmann, I still vividly remember their names. They said they came up with, and they called it cold fusion. There's movies out there about this. They said they were able to do fusion at room temperature. Do you realize what that would do to the scientific world? People will go nuts. If you could do fusion at room temperature, we have more power than we ever need, and that we'd have no worries about anything. None of that. Our lives would just be absolutely much smoother that way. Okay? So the first time Dr. Pons and Dr. Fleischmann were to speak was in Dallas, Texas. And lo and behold, my college sent me there. You know, I'm a snot-nosed, arrogant little turkey, didn't know squat in the world. And they had it in this huge convention center, and here's all the greatest minds in the world. Now, our government thought this cold fusion was such a great idea. They gave these guys at the time like $8 million and said, do more research. All right? And I don't want to really go into what they said they'd done, but they used the element gadolinium, and they were able to fuse. Gadolinium has like a cubic, like gadolinium. It's atoms. It forms like a cube. And they said they were able to force hydrogen together in the spaces and make helium. And they could do it at room temperature so it wouldn't melt the container. It would be perfect. And I mean, everybody's just like, this is the greatest thing ever. So our government gave them money, and all the labs, Stanford, MIT, all these great places were trying to replicate their results. And I listened to them the first time they spoke, and I'll be honest, a lot of it was over my head, but it was amazing to hear people, and people were very negative. It was very cynical questions like how. And so all these labs are trying to replicate these guys' results. You want to prove it, that you could do it. It was fake. It was fake. They couldn't do it. They took the $8 million and they ran. They have not been heard from since. Now, you got to be incredibly smart to be able to pull off a prank, not a prank, but a con like that. Okay, cold fusion does not exist. Jerks. I mean, it would have been awesome. Okay? All right. Next thing. Test stuff. Fusion, done. Fusion, done. Tomorrow, there'll be either some definitions that you have to write out, or there'll be some definitions like using multiple choice. Here's what you need to know. Okay, this is test stuff. You need to know alpha, beta, gamma, neutron. You need to know their symbols. You need to know their penetrating power. It's all in your notes. Let's throw in positron while we're there. Okay, so those are all the particles. You know what a chain reaction is. Also this is all from a nuclear power plant. You need to know what a moderator is. A control rod. What a critical mass is. You can go back to old videos and look these up, or you can just look them up online. Come on, use your resources. You need to know the difference between ionizing radiation and non-ionizing. What else? Probably need to know what a nuclide is. Critical mass. You need to know when we do an equation, who's the parent and who's the daughter. You better know all about fission and fusion. Probably should know something about half-life. And the last two are similar. Transuranium elements and transmutation. Okay. So those are all definitions I think you should be completely aware of. All right. Next up on your test, you'll have to do some equations. So I'll ask you to do alpha decay, beta decay. I'm not going to go through them all, but I'm going to ask you to write the equation of either alpha, beta, positron, neutron decay, or I could ask you to do one where they capture a neutron or something like that. It's all in your notes. So you're going to do equations. You will probably be asked to do an EMC problem, E equals MC squared problem. Again, straight out of your notes. I definitely will give you a half-life problem. Okay, probably just one of these. I'm not trying to kill you here. Probably ask you something about carbon dating. Am I still on the paper? I'll ask you about a fission nuclear plant, fission, and I'll ask you about fusion. Okay, there's your test stuff for tomorrow, which is Tuesday. Okay, last thing I have for today, and I'm going to shut up and be done. I know I'm boring you. I didn't even give you a joke. I didn't give you anything. The homework I'd like you to try tonight, okay? It's called Shot to the Heart. I happen to have the radio on. It's a Bon Jovi song. 28 through 32. They're quick, they're easy. I would like you to look at problem 33. Just look at it, okay? That's your homework. Tomorrow I'll have the test, okay? All right, peace out.